So, can you check that it's working properly?
Yeah, I will check it.
That's great. So, получается, начинаем? Okay, so today's talk will be on Pendragon thumb, isomorphism, and in general unoriented bodisms. So let's maybe start that with the definition of what unoriented bodisms are and some motivation, and then we'll give a more concrete outline for the whole talk. So yeah, before that, I should probably give some references. There are excellent notes by Miller. So this talk will mainly follow chapter 1 of this book. And there's also, let me spell the author correctly, Milkevich. Milkevich, also called like unoriented bodism. So this is broadly similar to the chapter 1 here, but these two texts, in my experience, nicely complement each other in the sense that the parts that are skipped in the exposition in one source are better covered in another source, so you can combine them to get something more of a whole picture. And the important thing is that here the author computes the unoriented bodism ring and star. I will explain what it is in a minute, and this should be something like the dream result towards which we will work today. So here author does not compute it explicitly, but they get most of the pieces in place, so you can kind of guess what it will be based on the first reference only. Okay, so with that, let's start with the talk proper. So the first part, unoriented bodisms. So recall that if you have a manifold, any manifold M, it gives rise to its fundamental class lying in homologies, upper homologies. Let's denote the dimension by n of M. And obviously, if we take integer coefficients here, this is not true. We need orientability of M. I'm sorry.
What does it mean, Hn level star?
Oh, sorry. Yeah. We would need orientability if we wanted to put that here. So we don't want to bother with that. And the word unoriented in unoriented bodisms mean that everywhere in this work, in this talk, we shall work with z by 2z coefficients only. And in the following, when I write homologies or cohomologies, I will always mean them to be in the z by 2z coefficients field. So each manifold gives rise to its fundamental class, and moreover, if we have a manifold M mapping into some space X does not need to be a manifold, any space will do. We have F lower star of M lying in the, again, nth homology of X. So in the sense, you see that manifolds represent homology, but obviously two different manifolds do not have to represent two different classes. In particular, suppose we have M, like if M is a boundary of another manifold of dimension n plus 1, Then we obviously get a diagram like this. So we have Hn m goes to Hn, here n plus 1, sorry, Hn m, just a boundary map from the long exact sequence. Here we have Hn plus 1 x whatever, m, and here we have Hn at x. So here again boundary map, and yeah, suppose that we have m being a boundary, and to extend this case of so-called singular manifold, a manifold equipped with a map to some space, we say that exists f from W to X extending f. Okay, so we get a diagram like this. It obviously commutes. You can check it directly. So, and you can see that, well, the image of the fundamental class of W goes to the fundamental class of M and goes to M here. Yeah, but on the other hand, we can get that as a boundary of something in the previous grade. So obviously,
What is Fm in the top?
yes, sorry. It would be better to put something like yeah, okay, maybe we can just put X here. I'm not sure. Okay.
So this is 0.
Yeah. Okay, what do we need to put here?
Well, this. Well,
Yeah.
So we could put x after the comma, and then we.
Yeah, then we'll get this map routing through 0. So
Then we get 0.
yeah.
So with xx, this shows that
Yeah, this gives us what we need. Yeah, right. Yeah, so this commutes, and we get the following. We get like the fact that if M is a boundary, then it represents 0 in homology, and obviously we can extend that to like this is M being equal to 0 in some sense, and we can extend that to two manifolds being equal to one another in some sense. So if we have M and N such that M disjoint union N is a boundary of some manifold W of dimension n plus 1, then M and N represent the same element in homology. Here, the important thing is that we don't have to bother with orientation, with minuses. Everything has order 2, because we are working in F2. In particular, obviously, it's actually can be seen directly that M as an element here has order 2, because, well, the joint union of M and M is just the boundary of the square, the product M times the segment. So all of this leads us to the definition. We say that M is null burdened, and analogously we can say that the manifold M equipped with a map to X is null burdened. Yeah. Let's say in this case if f star M Yeah, because the first case is actually a special case. We have a terminal object, just a point in our category, which means that every manifold M can be considered as equipped with a map from itself to a point. So basically, the first case is just a special case. The first case is just a special case if X is a point.
Okay, so let's define what is a group sub X. So if we
So we define
let's
M.
first explain what we actually want to construct. We want to construct a homology theory, which takes an X and
Yeah, right. I'll get to that in a minute. I just want to put the definition down. Okay.
yes, it's up to you, but I would like the public to know where this is going.
Okay. Yeah. So we just restate this property as a definition. We say that a manifold is null bordant if it is a boundary of something from higher dimension.
Okay, so let's say this once more. We fix an X,
Mm-hmm.
and then we consider couples
Yeah, so
M comma F, where M is a manifold and X is F is a manifold.
yeah,
And then we want to say when those couples are null, and this is the
yes. So yeah, it's important to understand that these are two different things. For example, a manifold M itself, say like a circle S1, is obviously null bordant. You can just fill it to obtain a disk which has boundary S1. So S1 is null bordant in the first sense, with X being a point. But if you say, for example, if you take X being S1 times, I don't know, R, then the embedding of the circle into this cylinder, yeah, you can just take the disk and fill that.
Yes, here X M is a manifold.
Yeah, here M
Is compact and it's
yeah, compact smooth manifold, yeah. As usual, so we can. Mhm.
But X can be other.
Yeah, X does not even have to be a manifold, let alone compact. X is just a topological space, something which we can define like homology of.
So this is not just about studying manifolds and telling which of them are the boundaries of which. It's also about studying X's.
Mm-hmm. Yeah. So with this, we can define certain groups which we'll later see form a homology theory actually. But for now, these are just groups. So we say that, this symbol is my attempt to write Gothic N, capital Gothic N. So this is
It's not something that they teach you in school.
yeah. Yeah, so this is just the set of manifolds, singular manifolds equipped again with the map to X factor by the relation of bordancy in the sense above. So we say that two manifolds are bordant if the union is null bordant, obviously.
So yes, M1 F1 and M2 F2 are bordant if by taking the disjoint union of the M's and the F's, we get something which is null bordant.
Yeah, yeah. Okay. So in particular, here, again, with x being equal to point, we have what is usually denoted just nth. We define it to be the Bayesian group of a point. Now, obviously, we have some operations here. For example, we have you know what? Actually, let's get some intuition about these things first. So, this Bayesian group, unoriented Bayesian group of a point, it's kind of a strange object. So, these are just manifolds without any informative maps, and we consider manifold to be 0 if it's a boundary of something. What is even like, are there any examples which we can understand that like a non-zero in this group? So is there any manifold which would not be a boundary of something?
Well, let's stop here and ask the audience. Are there any manifolds, orientable or non-orientable?
Yeah, because
which are not the boundary of it.
maybe this is just a zero ring. We don't know.
Examples of manifold, as simple as possible, of manifolds which run that.
1 point.
Well, 1 point, yes, that's a good example, but
Yeah.
no example is maybe just some zero-dimensional phenomenon. So, well, in dimension 1, where it's just one manifold, the circle is the boundary of this. Very well. What about what about dimension 2?
Well, there is a fact that a boundary of a manifold always has even order characteristic.
Yeah,
So any
For example, yes.
so
that's a
any
great point.
manifold with odd order characteristic is non-zero.
Yes.
Yeah.
What's an example of such a manifold?
I guess AP1.
Well,
No, AP1 is just a circle.
AP2.
AP2, yeah. Yeah. So actually,
it's the simplest.
non-trivial, yeah, example. So there is a point and then there is AP2. So we see that the generators, the first non-trivial generator in like the first non-trivial group is in degree 2. Okay. So with that being said, let's define some operations which would turn the Bayesian groups of a point into a Bayesian ring. So if we have two singular manifolds MF and NG to the same going to the same X, then we can proceed to define a map from M times N F times G. So obviously this like commutes with all the relations that we have defined. So this map gives rise to a map of Bayesian groups. What?
So F goes where? From M to which space?
F goes from M to X, G goes from N to X.
Very well. So this product will go from M cross N to X squared.
Yes.
So if the operation.
Yes. So this is exactly what I wanted to write, in fact. So we have, I really tried to write it beautifully, but N, say, Nx times Nm. We don't even actually need to have the same x here and here. We have x here, y here, and we get a map to n plus m of x times y. Yeah, so this is not something smart, this is just an obvious map. And what is interesting is the simplest possible case when both x and y are points, because then we get a map from in particular the map from the Bodism group of a point to itself with the degrees behaving in an obvious way, which makes it possible to define a ring by putting together all of these groups with an operation we've just defined. Okay, so this is what's called an oriented Bodism ring. Let's say that this is a definition. Okay, so this is the point where we stop and ask ourselves, what do we want to do in this talk? What are the objectives that we're going to try to achieve? There are two of them. So in the first part of the talk, I will construct what's called the Pendragon-Thom map, given the isomorphism between these kind of like strange objects, Bodism groups of space X, which we don't have any information about at this point. We don't know how to compute them. We don't know like how to think about them. The Pendragon-Thom isomorphism will say that these groups are isomorphic to fundamental groups of a very particular spectrum. And in the second part of the talk, if we have enough time left, I will try to at least work towards computing this unoriented Bodism ring or point. So these two parts will be very different in terms of the methods that we use. So the first part, constructing Pendragon-Thom isomorphism, is very elementary in a sense. It doesn't use any advanced machinery. We'll do the things just by hand, geometrically, and so it will be mostly self-contained. We'll only need a few like general boring theorems from differential topology, which we'll just use as a given. But on the other hand, the computation of an oriented Bodism ring is like a daunting task. It requires a lot of machinery that is probably not familiar to, maybe not familiar to all of the people here. Like we'll need Steenrod squares, Steenrod algebras, Stiefel-Whitney classes, we'll need Hopf algebras. So there are a lot of things, and we'll try to like work our way towards these computations, keeping some proofs, and hopefully we'll at least see why the answer is what it is. But okay, having said that, maybe yeah, let me erase that. And let's start with our second objective, constructing the Pendragon-Thom isomorphism. So for that, before we construct the map itself, we'll give a quick primer on vector bundles. Okay, so what do we need to know here? Okay, any manifold obviously comes with like any manifold can be embedded into Euclidean space. Say this is n-dimensional, and we embed it into R n plus k. This embedding always exists for large enough case, but obviously this is not uniquely defined. We can take different case, we can take different embeddings for a given dimension. So this is not something like concretely defined by a manifold. Okay, given such an embedding, we can, again, this is like a boring result from differential topology, we can always form a normal bundle to this embedding by, well, we take a trivial bundle, which is a pullback from here. We take tangent bundle and factorize, and we can actually embed this bundle into R n plus k, which should be thought of as a tubular manifold, a tubular neighborhood of the manifold M. So the fact is that we have such a commutative triangle, which is thought of as like we have a manifold, and we can embed a small tubular neighborhood into R n plus k. Okay, so yeah, now that I'm writing here nu to denote normal bundle. Okay, so is this thing at least somehow correctly defined? Is like if we fix the dimension, is it possible that we get two different normal bundles? Yes, in fact it is, but again, from differential topology, we know that this is just an artifact of low dimensions. For example, in R3, we can have like non-trivial nodes, embeddings of S1. This is trivial, but yeah, if you try, you can draw a non-trivial node, I believe. Okay, but obviously all such embeddings become equal, become just trivial when you go one dimension higher into R4. So we have a theorem, a general result from differential topology saying that yes, for a given dimension there can be different embeddings, but they are all stably isomorphic. So if we have nu1 and nu2, then there exists a large enough n such that nu1 plus the trivial bundle of degree n is equal to nu2 plus n. Okay? So what this says in our case is that although this normal bundle isn't uniquely defined, it is well defined in a stable sense. We have different possibilities, but they all become equal when we make k tend to infinity, when we take k large enough. So in all of the following, so what I just said is that we can correctly define in a stable sense, stable normal bundle of any manifold M. So yeah, this is more or less everything that we need about vector bundles. And now just a few more things which we'll use in the construction. So it's, I think, nice to have them laid out in, before that. So we'll also need a concept of one-point compactifications. Recall that if we have any space X, we can proceed to construct its one-point compactification X plus, which is in a set theoretic sense just X with one more point, which will often denote as infinity, but whatever. So I will not recall the definition from the classic topology, everyone knows that. What's important though is that whenever we have an embedding of y into x, we can we automatically get an embedding, not embedding, but just a map, sorry, between the compactifications going in the other direction. Okay, from x plus going to y plus. How can we construct that? Well, obviously on the image of y, we just take the inverse map, and everything not lying in the image of y, we can just map to infinity. Yeah, great. So this is just
It has to be open embedding.
yeah, open embedding, sorry. You are completely correct, and thank you for that remark. Open embedding. Yeah, great. And we will mostly be interested in one particular case of this situation, general situation. So, as we have seen here, for a normal bundle, we have an embedding E at nu into R n plus k. Yeah, open embedding, nice. So we can see what this construction gives us in this case. So what is R n plus k compactified? This is just S n plus k, the sphere of the same dimension. And what is E at nu compactified? Well, this is just something that we have seen already in this class, not in this lecture. This is just Thom space of the bundle nu. So we see that whenever we have a normal bundle on M, we can like automatically get an element of Pn plus k of the Thom space of nu, right? We got a map going from the sphere to this space. Yeah, so this is the beginning of the construction actually. So now we'll just have to start from this point and work towards the Pendragon-Thom map. Let's erase this. So here I'll kind of draw a large commutative diagram which will add some parts in the will add some parts to it in the process. So the construction is like kind of long, but every step in it is more or less obvious. So yeah, let's start. We begin with as we have said, a singular manifold M equipped with a map F. We choose some normal bundle nu on it, and yeah, I haven't said that here, but obviously we have the result that all the vector bundles on some space are classified by maps from this space to what's called BO of the same degree, which is just infinite Grassmannian if you want. So we can choose a map classifying this bundle. So yeah, say nu has rank k, okay. Going to be okay, and over this we have the universal bundle, which will denote xk from its total space. Yeah, this is just a tautological bundle on the infinite Grassmannian, if anyone wants like the concrete description of this space. Okay. So we have this map. Let's denote it. Let's also denote it nu, because obviously these maps correspond uniquely to yeah, we have this commutative square. Now, let's multiply both of the things here by x. So the maps are defined in the only possible sense, in the only possible way, sorry. So we have here nu times f, mapping from M to a product. Yeah. So we get a square like this, and let's now look at what this space is. Obviously, X is just the total space of the trivial bundle, of the zero rank trivial bundle on itself. So this is just the total space of the product of bundles xk times 0x, right? So far we haven't done anything like interesting. We are just doing all those things. Now the interesting part, let's look at the upper row of this square and apply like, let's thomize it. Let's make a step from the total space to the thom space. Obviously, we have a map of bundles xi to eta. We have a map of thom xi to thom eta. Well, how to define it? Define it in the only possible way on the bundles and map infinity to infinity. Check that everything is correct. So, okay.
This map would need to be injected in each fiber.
Yeah, that's a good point. Yeah. So let's. Yeah, let's do it like that. Yeah, this map will have to be injective. Luckily here, this is the case. Okay, so let's apply this construction to the upper row and get the map from thom space of nu to thom space of xk times 0x. Okay, and now the last step. Let's look about what this space is. So, in general, suppose we have two bundles like xi and eta. Yeah, and we take the product and we take a thom space. Is there any way how we can like?
Well, we've already used it in class several times.
Mm-hmm.
So it will remember the answer. Does anyone remember the answer?
Yeah. Huh? Yeah, the smash product. This is actually even more general than just taking thom space. If we have, like, this is xi times eta, yeah, and we need to take a compactification. So if you like draw it geometrically, it becomes completely obvious. So you have like x, you have y, and you have
This compactification thing
Yeah, okay, so this is actually true even in the general case, but if the bases are compact, we can get this fact for free as a consequence of the more general result about one-point compactification, so, no, the one-point compactification of the product of two spaces. So yeah, if you draw it like this, you'll see that the compactification of a product is the product of spaces, but all of these, like letter L, will have to be compactified into one point, smashed into one point. So yeah, we have that this is some C smash some eta. Yeah, great. So let's apply this here, and we get what? Get this is some ck smash, and again, what is some space of the trivial rank 0 bundle? Well, this is just X with a single infinity point because we have to compactify. So this is some C smash X plus.
Yes, if we collapse the empty set, we get an extra point.
Yeah, but you can think about it as, you can also like imagine it as the total space of this bundle being just X, and then you, yeah, okay, in case of compact X, and you 1 point compactify. Yeah, so we get a map from here to here. Let's like define MOK to be this very thumb space of the universal rank K bundle of a BOK. This is a very standard definition, so it's not something like made for this talk. This is a very basic thing. Okay, so this can be once more.
Okay, so moreover, we know that there's ML of K
yeah, form a spectrum. Yeah.
form a spectrum.
Yeah, we will.
This is something we saw a couple of times.
Mm-hmm.
In
Yeah, and that's great because we'll need it when we prove that this map is well defined, because we took some particular normal bundle here. We'll have to prove that it survives under stabilization. Okay, so we can rewrite that as MOK smash X plus, and as we have seen, we get a map from some new to here. And then, well, the whole point of this part of the board was to prove that whenever we have a thumb space of a normal bundle, it comes equipped with a very special elements of it, its homotopy groups. So we get a map from Sn plus k here, right? So this diagram is the end result of all of this diagram chasing, if you will. Well, there's no chasing, just diagram construction. And what does it say us? In the end, it says that given MF, we somehow taken some choices in the process, but somehow constructed an element of Pn plus k of the space MOK smash X plus. Okay? So this.
So now
Is great.
Now we see something which resembles what we've seen quite a few times in this.
Yeah. Because what are these things?
So,
Okay.
let's ask the audience, what are those things?
The homology with coefficients in the spectrum.
Yeah.
Well, not quite, but if we let k go to infinity, we get precisely the homology groups of X as a space with coefficients in the spectrum.
Yeah, so this does resemble, the definition of homology. but for now, this is a particular element, not like an element in the limit, so not a stable element. But you may probably already guess it. We have said before that we don't have the normal bundle defined, well defined in any particular dimension, but we have it well defined in a stable sense. So now we have defined a map, and now we will stabilize it. We will prove that we have a sequence of such maps for all directions, and when we take a limit with k going to infinity, we will have a well-defined element nu, uniquely defined element nu, and so we'll get a uniquely defined element in the limit. Okay?
Well, perhaps it's worthwhile to say exactly what the quadriagonton theorem says, and then our task will be to prove this thing.
Yeah, that's great. Let's do that. So the map is constructed. We just have to prove some of its properties that will establish the following result. So theorem, that's main result of part 1, which says that the unoriented cobordisms of X are isomorphic to well, let's put a star here,
Or which is the
Huh?
just
Oh.
just
Sorry.
Or in other words, it's
But we have not defined what this is. This is kind of a no definition.
it's either pi lower star of MO smash X, or
Yeah. So that's exactly what I said. We have to define where. Okay.
Но это то же самое, что это тоже второй равенство. So this is the same as ML lower star of X.
Yeah. Sorry, I messed everything up. Yeah, thank you. So which is this is a theorem, and this is just like the obvious thing with correct definitions, which is just MO star of X.
So
Yeah.
the second, the last part of this is just a way to denote the.
Yeah. This is just the definition of homology of spectrum with coefficients in another spectrum, which we have established before in the class. And the theorem is this isomorphism. This is what's called Pontryagin-Thom isomorphism. And this is the map that we've defined after stabilization.
Yeah, so we have a candidate for a map from
Yeah.
from the right from the left to the right, and we need to check a few things.
Yeah. That's exactly the case. So let's save that for the future and proceed to checking these things. Yeah.
Yes,
So
we need to check that this is well-defined.
Mhm,
It's
mhm.
it's additive, so it's a map of groups, and it's objective and subjective.
yeah. So the first thing is let's actually stabilize that. So let's prove that if we take let's prove that if we take increase the dimension by taking by taking sigma of everything, we will get the same thing as if we would choose to work not with the original normal bundle, but with the corresponding normal bundle in higher dimension. So let's put that down formally. We have, if we decided to work in one higher dimension, we would get a map from Sn plus k plus 1 going to some nu plus 1 going to mo k times x plus mo k plus 1 times x plus, right? On the other hand, we could just take sigma of everything in this sequence. So sigma Sn goes to sigma sum nu goes to sigma mok times x plus, right? So we have the obvious map here. And now we prove that we have to prove that we have maps here and maps here. Let me put question marks alongside them for now. We will now establish these maps. Okay. Let's begin with this one. So this also exists for general reasons. Again, take the thumb space of nu plus 1x. Here the plus denotes the direct sum of two bundles over the same base, right? So we can rewrite that without actually changing what's written, just another notation. We can say that this is a product of two bundles. We have nu and we have rank 1 bundle over a point, right? So this is a product in a sense that we have two bundles over different bases, and then we can form a product bundle over the product of bases. But the base here is just a point, so yeah, so the product is just x again. Now, by the property that we have used here, this is just sum nu wedge smash sum space of the rank 1 bundle over point. But what is this thing? Well, it's just S1. Okay, so you have a point, you have rank 1 bundle over it, and then you compactify, so you take an infinity point and compactify this, so this is just S1, okay? Uh-huh.
On which space the bundle what's the base space?
Yeah, nu is everywhere in this argument. Nu is a normal bundle over M.
But where x is like the last equality, we have sum.
Oh, yeah. You are right, of course. Thank you for pointing this out. Of course, M. Yeah, sorry. Thank you. Okay, so now this makes sense, right?
Yes.
So this is just sum nu times S1, which is just the suspension of sum nu. Okay, great. So we have defined, not only defined this map, but we have proved that this is an isomorphism. Let's use the usual notation. Great. So the first two maps are done, and now all that remains is to show that this map exists, and then to show that all of this commutes. But commutativity is like trivial because all of these maps do the same thing. Yeah, so how to define this? Yeah, well, take we have MOK. Over this, we have the universal bundle CK, but we can actually take add one trivial component to it. This will again be some bundle of rank k plus 1, right? So this is classified by some map to MO k plus 1 and CK plus 1 here, right? This is just general theory. Yeah, we obtain the map going. Sorry. The map CK is over BO, and it's classified by the map to BO of k plus 1, not MO. This is just me messing up the notation. Yeah. So now we look at the map of total spaces, and again we take some space of both of them. So we obtain the map from some CK plus 1 to some CK plus 1, right? But now this is just MO k plus 1, and this, as we have just seen, is sigma suspension of MO k. Great, so we get a map from the suspension to the next step. Yeah, right, so the diagram is defined, and all we have to do is check that it's commutative, but well, in a sense there's nothing happening in this diagram, so let's look and try to make a sense of what's happening here. We have originally had an embedding of M into some Euclidean space. We had a normal bundle here, and now what we wanted to do is add one more axis to the picture. So consider this as an embedding into not R2 in the case of the picture, but R3. So increase dimension by 1, right? So we had a normal bundle in the plane. Obviously, to make this a normal bundle in R3, in R n plus k plus 1 in the general case, we just multiply it by a normal map, a trivial map, which makes increases the dimension of every fiber by 1. Yeah, so this is this map, and yeah, well, and now suppose we want to compute, for example, that this square commutes. So recall that how we got these maps from the sphere to the Thom space. So we said that we get an embedding from, well, the manifold and its tubular neighborhood drawn here into, well, just a plane or a space, and then we compactify it. So we obtain, by compactification, a sphere, and we get a map in the reverse direction to the Thom space. What I want to say is that, yeah, if you look at that, in the first case, in the upper row, you have a sphere of one dimension greater, where the original space is embedded as an equator, because of how the plane was embedded in the space. So this gives us exactly this map Yeah, and when you look at the thumb bundle, you see that again we have this map with the original thumb bundle embedded exactly as the like middle layer, the equator of the suspension. So again, we have this exact isomorphism that was written here. So yeah, this commutes. And the same thing actually happening here, except that we are not even interested in, yeah, we have this x component, but we are not even interested in here because this behaves the same. The map to this is given by f, which is the same in all dimensions. And all that happens is that we increase dimension by 1, and we increase the classification map by 1 also. So the commutativity of this square is just naturality of the classification map, basically. And yeah, it follows from general result. Okay, so this commutes. What does it give us? This allows us to stabilize the map in question. Let's refer to this as PT, okay? Pendragon thumb map. So from PT, from the map in the given direction, we now get a map from MF to the limit of k going to infinity of p n plus k, and here we have MO k smash x plus, right? So yeah, now in this we see exactly the definition of the stable homotopy group pk of MO smash x plus. Yeah.
Okay, so we constructed a map.
Yeah, so we constructed a map in question.
From the left-hand side to the right.
But there are two things now left to check. First is that we have constructed a map from a given manifold, not from Bodgism class. So we have to check that it depends correctly, like that null Bodant maps, null Bodant singular manifolds go to 0, right? This is the thing we will have to check next. We will be checking next. And then we have to construct the inverse map to get that this is not just a map in one direction, but actually an isomorphism. So there are two things to check.
We also need to check if we get a map of Euclidean groups and not just subsets.
Yeah, well, that's true. We would have to check that when we take the disjoint union of two manifolds, which represents addition in the Bodgism ring, we obtain the sum in the homotopy group. But yeah, well, this is actually kind of trivial because by the definition we would have to work with the disjoint union of two manifolds. So we'll just have two different normal bundles, like one manifold, another manifold. And then when we take Thom compactification, we obviously get the common point, and here we'll have, yeah, I don't know how to draw things, but we'll have one Thom space, another Thom space, which do not interact with each other at all, except for intersection at one base point. So yeah, when we proceed with this construction, we'll get that the spheroid we got is just, yeah, two spheroids not interacting with each other, one for one manifold, another for another manifold. And this is exactly the definition of addition in homotopy group. So the fact that this map preserves the sum structure is actually kind of trivial. So the two interesting things to check is that null Bodant maps go to 0. This is arguably the hardest thing in the whole proof. And another thing is to construct the inverse map. yeah, which also requires some work. Okay. So let's erase these two parts. Yeah, so we now have the Pentragon-Thom map written down there. I can erase this without worries. Okay, so as we have said, two things to check. First, that the map we constructed preserves the equivalence relation in this group, and another to construct the inverse. So first, suppose M is actually the boundary of another manifold, and there exists the map F. Extending F, right? We have to prove that in this case, after going through this sequence of maps, we get 0 in the end. We get the 0 element of the homotopy group. So this is where the geometry comes into play, where we have an actual interesting picture.
And it's a good time to have a break.
Yeah, okay, so I think that it would take us another 20 minutes to finish the part 1. So yeah, I think it would make sense to pause here.
Let's have a half an hour break until 10 past 6, and then we'll continue.
Okay. Do I somehow turn it off? Or?
Yes, so you need to open the box.
Uh-huh.
There will be a button in there.
You just close here.
Thank you. Yeah. So let's recall where have we stopped. So our goal is still to prove this Pendragon isomorphism theorem, and we have come pretty close to that. We have defined a map going from the left side to the right. We have two things to prove that are left to prove. First, that this map is well defined in the sense that it respects the equivalence relation imposed on the left. So that is to say, if a manifold is null bordered, then we have to prove that it corresponds to 0 in homotopy. And the second thing is we'll have to prove that there exists an inverse isomorphism to construct it, and then we are done with that. So let's proceed. First, suppose that some manifold is null bordered. That is, we have a map F capital, capital F extending the original map F from M to X, and yeah, the map from W to X, and M is realized as the boundary of W. We have to look at this composition and prove that it is 0. So yeah, here we make use of another general but more or less obvious result from differential geometry, namely like theorem. For any embedding M into S n plus k, we can extend this to the embedding of W into the disk n plus k plus 1. Yeah, such that obviously M is yeah, exactly the, yeah, let's name them I don't know, I smaller and I greater. So first, M, the boundary of W, is exactly its intersection with the sphere, but also we have some even nicer properties. We have that the tangent space of W is not contained in the tangent space of S. Yeah, for any points of intersection. So what this says is that if you have an embedding of some boundary of a manifold in a sphere, we can extend it to an embedding of the whole manifold yeah, in geometrically nice way. So
don't we need to suppose that K is sufficiently large?
yeah, yeah, obviously. So everywhere here we are using with we are working with sufficiently large. Yeah, okay, so let's just add that. Yeah, obviously. In low dimensions, as I said, for example, with knots and something like that, we can construct like counterexamples, but when the dimension gets high enough, everything simplifies to the only possible trivial case. Yeah. Okay, so we can extend an embedding of M to an embedding of W. We're now going to utilize this fact to prove that, yeah, the is null homotopic. So let me try to do two things in parallel. So we are going to simultaneously write the commutative diagram that we will use to prove null homotopy, and I want to simultaneously try to explain what's happening geometrically. So I'll try to draw a concrete example in low dimensions. So low dimension. So what did we do to construct this Pentragen-Thom map? We started with an embedding of so I'll take M to be just 2 points and W to be the line connecting them. This is the highest dimension I can get and still draw it on the blackboard. So we started with an embedding of M into some Rn, in this case just embedding into a line, and we considered a normal bundle. Yeah?
Are we trying to prove the theorem?
We are trying to, no. This theorem is just a given thing from differential geometry that we are using in the proof. We are trying to prove that Pentragen-Thom maps respects null bottoms. Okay, so this is just something that we use in order to construct null homotopy for this map. Okay. Yeah. Okay, so we started with an embedding of M into a line. Now, in the process, we had to compactify this line to obtain, in this case, a circle, and we get the map from this circle to the Thom space of this normal bundle, which can be visualized like this. So we have the infinity point. Here we have two small neighborhoods, and then to construct the Thom space, we take anything besides this point and map all of them into the infinite point. Okay, so this is the visualization of the map from the sphere to the Thom bundle, the Thom space of the normal bundle that we have constructed earlier. Now, in our case, the situation is more interesting. When we look at this, so as you can see here, we obtain an embedding of M into Rn, which can be thought of as embedding of M into a sphere. So let me redraw this. We have a sphere. Here is a chosen infinite point, and here we have an embedding of our manifold. Now, using this theorem from differential topology, we know that we have an extension of this embedding to an embedding of the whole V into the disk. Yeah, so here I think about this as a square, and now I fill that up. So I obtain the whole disk and an embedding of yeah, and obviously I haven't said this explicitly here, but in this case, any normal bundle on M can be thought of as the restriction of a normal bundle on W to the sphere S n plus k, right? So here I have a normal bundle on the sphere, normal bundle to M, and I extend it to the normal bundle on the whole W, right? So this is the disk W, the intersection gives a normal bundle on M, and we have an obvious embedding here. Yeah, right. And now, when I go from here to the Thom space, how do we visualize that? Here we get again just these two leaves corresponding to the neighborhoods of these 2 points. But here we smash everything besides this bridge into the infinite point. And if you think about it, what we obtain is this this seashell shape, which the Thom space of the boundary is exactly like the boundary of. So here we have the outer two loops of this thing. Yeah, and here we have a map. These two are just taking Thom space. This is an obverse embedding. This is also an obverse embedding, right? So geometrically, the picture is trivial. Let's now just formalize this. So formally, we have the map S n plus k going to the Thom space of nu. This is just the map that we have constructed before. Now, yes, so let me denote this as nu, and the normal bundle on the W I will denote as nu tilde. Just I have to denote it somehow. Yeah. So here we have an embedding of the sphere into the disk, right? B n plus k plus 1. And now here, what do I have here? I have Thom space of nu tilde. And now this is, not embedded, obviously, just mapped here. This is embedded here. So I get a commutative square like this, right? And now to complete the definition of the Pendragon Thom map, I get I have to give a map from the Thom space of nu to MO. So here we have a map to MO K smash X plus, right? So now, if we were so lucky as to have this map here, making everything commutative, then we see that the top row becomes null homotopic because it has to pass through the disk here, which has zero homotopy. Okay, so all that remains is to show that yeah, we have this map here making everything commutative. What is this map? Well, there is only one thing that it could be. The nu tilde is a normal bundle on the manifold W, which has a map mapping from it to X. So this is a singular manifold, and we can construct the proceed with the construction of the Pendragon Thom map, just starting not with the bundle eta, but with not with the bundle nu, but with the bundle nu tilde. So in that way, we get a map from S n plus k plus 1 to Thom space of tilde tilde nu, and then we get this map. We now just have to prove that this triangle commutes. But yeah, well, this is obvious.
So,
Mhm.
tilde is a normal bundle to embedding of manifolds with boundary, W to the
Yes, nu tilde is the normal bundle on W, right?
yes.
Which restricts, when we restrict from disk to the sphere, nu tilde restricts to nu. Okay? Yeah. So I want to now prove that this triangle commutes, right? To do that, let's recall how exactly have we constructed this map. So if you remember the diagrams from before, well, we had a classifying maps from M to BOK, and then this map was constructed in the following way. We have total space of the bundles like here. We have a map between them, and then we thomize this map, take some spaces of both of these total spaces, right? So the important thing is this starts with the map from M to BOK smash X, obviously. Yeah. Cross X, sorry. BOK cross X, and here we have a classifying map of nu and the original map F from M to X. Now, if we proceed with the construction of this map for nu tilde, we get here the map from W to BO K plus 1 because, oh, no, BOK, sorry. The disk is has one dimension more, but W also has one dimension more. So both N and K in the construction are increased by 1. So here we have BOK again, yeah. And yeah, here we have nu tilde, and here we have F, right, cross X. Yeah, so the maps here are constructed as the corresponding maps of total spaces. But well, here we have the commutativity, right? If we take just the identity map here, so this collapses to the single node, and the inclusion map here, M is included into W as its boundary, then this commutes. And when you, like, starting from this triangle, you lift everything to the total spaces of all the bundles, then you take thom spaces of all the total spaces, and you get exactly this triangle. So since you have started from the commutative situation, you have commutativity here, like, right? So this is what we wanted to prove. We have Pentragen thom map for nu on the top. It is null homotopic because we can alternatively traverse this diagram going through the disk, which is homotopic to a point, homotopy equivalent to a point, right? So if M was a boundary of something, then it goes to 0. Yeah. One thing proved, one thing left to prove. Is everything okay?
Let's ask the audience. Is everything okay? So what do you think the answer is?
No, you were just staring at some part of the board. I thought maybe you had questions. Yeah, okay, if there are no questions,
Okay, let's ask Misha. If Misha doesn't understand, then not Misha.
Is that everything so far in this plan has been very clear?
Okay.
Yeah, thank you.
Then let's at least assume that for the rest of the class, it's more or less okay as well.
Okay. So extending F, then Pentragen thom map of M is 0. So this thing we proved. And now how to construct an inverse. Right? This is the last thing that we have to prove here.
Why? So then we would also need to check that both compositions are the
Yeah. So I include that into this construction. Yeah, we can also probably erase that and use this part of the board. I don't know. We probably won't need that much space. But who knows? Okay, so as usual, this will be like the direct construction, but now we are given something. We are given a homotopy class, a map which is given only up to a homotopy, right? And we have to construct a smooth manifold. So yeah, so here we'll have to make a transition from something not uniquely defined only in homotopy category or whatever, to something very concrete like the smooth structure. So as usual, we will have to rely on one result from differential geometry, which is once again obvious if you like follow the proof, but we won't follow the proof here because it is differential geometry and not algebraic topology which we are studying. So what is the result? It goes like this. Suppose we have a pullback square. Here we have U, here we have V, and here we have a pullback. Suppose that these are smooth maps, inclusion of smooth manifolds into X, exactly as before, as the case we dealt with before. When can we construct a smooth manifold structure on this pullback?
So could you write that U, V, and X are smooth manifolds and
Yeah, X is not even necessarily a smooth manifold. Probably, no, probably, yeah, sorry. All of them are smooth manifolds. So the question is like this. And the answer coming from the differential topology again is this is a smooth manifold if the maps are transverse at every point of intersection. So what does it mean? It means that for any x, like for any u, v, such that, yeah, let's name them fg, such that f at u is equal to x equal to g at v, we have tx, yeah. Yeah, we have an equation like this. So this is a tangent space to the image of u. This is tangent space to the image of v, and yeah, the sum is not necessarily direct because they can intersect not over a point but over a submanifold or whatever. But the transversality means that the images together form the whole tangent space of X. Okay, in that case, we can guarantee that we can like pull back the smooth structure to the cross product. Yeah, so this is again the result which that we will just use, and we will now employ it to construct a smooth manifold as a pullback of something. Yeah, so how do we do that? Let's note that the space, yeah, so start with a map G from S n plus k to Pn plus k MO. Again, always k is meant to be large enough.
So should it be P because we already map a sphere, like we map a sphere into a space?
Oh, yeah, sorry. Obviously. So we want to construct the map, the manifold M corresponding to this map, this homotopy class. So observe that we have the following identity: MO k slash x plus is actually equal to MO k times x factorized by like point times x. Well, this is just the definition of the smash product in the particular case when the right summand, one of the summands is 1-point compactification, right? So from this space, from this description of this space, we can see that the first projection from these two MOK is actually well defined, right? Because we do not factorize any elements. We don't glue any elements of MOK together. We only glue some copy of X into 1 point. And well, when it comes to the second projection from these to X, this is everywhere except infinity, right? So if the part of the space, of this space that we are interested in does not intersect the infinity point of X, like the base point, sorry, everything except base point.
Did you turn the microphone on?
It says that it's powered, but I don't really have any way to check. Okay, so everywhere except the base point, the second projection is also well defined. Okay. So now we want to do something like that. So we.
Okay.
That's great. So to do that, we will have to to prove transversality, and to use transversality related results, we'll have to go back to working with finite dimensional manifolds. So instead of MOK, we are going to need to use we're going to need to use finite dimensional approximation to this, which are just Grassmannians in large enough space, right?
So Morbus has to take the tautological bundle and
Yeah. Oh. I meant again. I messed up. MO and BO. I meant that instead of BO, which is just infinite dimensional Grassmannians, we're going to use Grassmannians in finitely dimensional Rn, but we are taking everything that needs to be large enough. We are taking it large enough, so we don't have to deal with the problems. We'll justify this substitution in a second. So, yeah. Now, we have the map G from the sphere to this space. I want to consider map which I'll denote G1, which is just a composition of first G, and then projection on the first summand. So notice that this G1 map is from the compact space, from the sphere. So it lands in some compact subset of MO. So although technically I don't work with MO, I have to work with some finite dimensional Grassmannian, it is still fine because actually the image of the map and everything we are working with here lands in some finite skeleton of BO and MO. Okay, so now let me draw the diagram here. I have the Thom space of the universal bundle XK. Again, instead of the usual XK, which is over BO, I take its approximation XKN, which is over Grassmannian. I have two maps into it. First is the zero section, S0, S0 from the Grassmannian, right? And another map is the map that we have just defined from Sn plus k, and we named it G1. Right, so I'm in exactly the situation described here.
Well, the Thom space is not quite a manifold.
Yeah, except for some problems. Like Thom space is not exactly a manifold. It has problems, but the problems it has are only around the base point, the point at infinity that all the layers, all the fibers converge to. Anywhere except that point, this is a manifold. So observe that this map is a map of the image of the zero section stays away from the base point, the infinity point, almost by definition. And in this map, we also have a well-controlled thing. The only point, like the point going to the infinity, is the base point of the sphere. So anywhere except those points, the situation is just a maps of compact manifolds or smooth manifolds, and well, another result from differential topology. Sorry, I forgot to write it down explicitly. But when we have two maps, we can deform one of them slightly homotopically so that the two maps are transverse. So basically, if you have one map and another map which are somehow turned out to be not transverse, you can just take a very slight deformation of one of them, and all the edge cases, all the not transversality will vanish. Okay, so here we'll have to deform G1 slightly so that it is transverse to the zero section, and then we can form the pullback square. So M. And this is not a coincidence. I claim that this M is exactly the manifold that we have to construct. So we started with the homotopy class G, and this is the manifold we constructed. We obviously also have to construct the map from M to X. How to do that? Well, just take the second projection. Well, but second projection is not well defined at the base point. That's not a problem, because here we have the map. Yeah, one more thing. This is an embedding, right? So by abstract nonsense reasons, this also has to be an embedding. Yeah, that's just the usual property of the pullback square.
It's like codimension K embedding.
Yeah. So M is an embedding into SNK in the sphere. we have the infinity point, which maps to the base point, which maps to the base point here, but elements of M cannot in any way reach this point. Why? Because the image of M here is equal to the image of M if we go this way over the diagram, and this way we land in the image of the zero section, right? So all points of M map into the zero section, away from the base point. And this is exactly the thing that we needed to check if we wanted to make sure that the composition of this map with with pr to g to x is well defined, right? So in this way we obtain a manifold M and the map from M to X. Yeah, we now have to check that this is inverse. Yeah, let's pick a direction. Let's check, for example, that if we start, checking, checking that first, doing PT and then PT в минус первой lands us in the same manifold M. Yeah, at this point, every construction has been laid out like concretely in very precise terms. So all we have to do is just analyze our construction and see that the result is actually obvious. So yeah, let's try to do exactly that. So yeah, we start with the manifold M. Remember, we take its normal bundle and embed it into Rn plus k, which we can then reverse by taking compactifications, obtaining the map from the sphere to the Thom space. Now, in the Thom space, yeah, and this then maps to the Thom space of the universal bundle. The construction went like that. So the question is, in this universal bundle, we have zero section. It corresponds exactly to zero section of the Thom space of the normal bundle. And what are the points of and the zero section of the normal bundle is just a manifold M, right? So suppose now that we have started with a manifold, we constructed this, we computed this Pendragon Thom map of it, and we got this map. We ended up with this map from the sphere to the Thom space. Now, we try to proceed with the inverse construction and define this pullback square. What exactly are the points we're going to end up with? These are the points of the sphere, S in S, right? Such that they image under this map lies in the zero section. Right, because this is the definition of the pullback. This is just the points of this space and obviously the corresponding element of the Grassmannian, but we can deduce it from the points, so no problem. Yeah, so these are exactly points of the sphere which have its image line in the 0 section. And what are these? We have seen from the construction that this is the 0 section of the Thom bundle. This is, and the 0 section of the Thom bundle is exactly M. So the manifold that we get in this way is exactly M. Well, technically, we have not proved that this is the same M because we only proved it theoretically. We proved that this is the same like subset of the this is the same subset of the sphere, right? But well, when we have an embedding of M in the sphere, the topology of M comes from and the smooth structure of M comes from the smooth structure of the sphere. So if we have the two manifolds are equal as a subset of the sphere, well, they have to be equal as manifolds. Well, because the smooth structures coming from the same place. Yeah, so we did this, and yeah, this was the geometric direction. And another direction is more like there isn't really any geometry. You just have to meditate on the diagram and see that this is exactly the thing. Yeah, the things are equal. Yeah, the question.
Like one subtlety that this map from S n plus k to MO smash x is not given to us. It's given only modular stabilization and homology. And like we should say something that if we have a homology of map, it corresponds to the properties of resulting manifolds.
Yeah. Yeah, so that's a very good point. Like, I cheated a bit. Instead of taking something line in the, explicitly taking the element of the limit of these homotopy groups, I just took an element of one of them. So technically, I now have to prove the same things that if I take its image in the one dimension higher, then we get the same thing and so on. And I actually don't want to do that. I want to, as you want either, if you are not convinced, you can explicitly consider this and as an exercise prove that the result will be the same. But I think that at this point, well, there aren't really any doubts. Yeah. Yeah, because of our liberty in taking these elements of the homotopy, of the limit, taking elements representing something particular in the limit of homotopy groups. Yeah, so yeah, we should probably also check that the other direction commutes. To do that, well, what do we have to do? We have to start with this construction, right? We are given a map, we constructed M. Now let's look at, let me draw again the diagram needed for constructing PT. It went like this. M BO times X nu. Here we have MO smash X plus, and here, yeah, sorry, so and here we have S n plus K. So this is the composite map, but now observe that it really is, it really consists of two different things. Like, we have defined this map separately, and then this map like separately. And the first part of this composition, the map from S n plus k to some nu, is really like a given thing. Like it does not depend on the geometry of the embedding M into X at all. This is just this map is just a consequence of the fact that any bundle is embedded into a large enough Euclidean space. So what we really have to look at here is this part of the diagram where we construct a map from the thumb space of the normal bundle into MO, right? Yeah, so what do we have to do here? 1 second. Yeah, so to see that, well, the map was defined as lifting, as a lift of the map we have constructed in the lower row, and the map in the lower row is just two maps. First from M to BO, and second from M to X. So we now have to check that both of these maps are exactly the maps that, we now have to check that both of these maps are exactly the maps that we have started with. No, wait a second, sorry. Yes, so we are now checking first PT and then PT inverse is equal to ID. So we start with the map from the sphere, then we make this pullback square, and we obtain the maps from M to X and the map from M to Grassmannian as a part of the construction of PT inverse. And then we use PT on the resulting manifold, and we have to check that we end up with G, right? So and the map, so we have to prove that this is G. Yeah. Yeah. Hmm?
That the top horizontal arrow is actually the approximation to specifying map.
Yes, yes. So we obtain here the map from M to Grassmannian. Actually, since everything is compact, we can assume that this is actually a map from M to the infinite Grassmannian, that is to BO. Yes. So
So it's not like we don't need any assumptions, we just embed this Grassmannian.
no,
map.
yeah. Well, we can post-compose.
The solid map
Yeah.
is precisely the specified map for the normal bundle.
Yeah, yeah. Yes, that's true. So yes, sorry, I kind of, like, the thing that we are checking does not require any, like, insights. It just requires juggling the construction a bit to see that we are really getting the same thing. And I kind of lost myself here. So maybe we can actually leave this as an exercise, because again, this is just requires to check that, yeah, we have this map from X, this map to be O given from this diagram, then we leave them, we obtain this map, and we just have to do a straightforward computation to check that this map from the sphere, the composition map, is the same as the original map that we started with. So yeah, let's actually leave that as an exercise.
We don't have time for actually computing the
Yeah, I'm afraid we would not be able to make significant progress there. How many time do we have left? How much time? Okay, let me just state the result then. I think that will be sufficient for today. So, as I said before, we have now computed that these Bodgism groups are just fundamental, like homotopy groups of this spectrum. So, what are these groups in case of a point? Like theorem. As an algebra, we have this letter again equal to F2 generated by like x2, x4, x5, etc. Namely, this is F2 generated by all x's with indices such that E is not equal to power of 2 minus 1. Okay? Yeah, and obviously the degree of xi is I. Yeah, so this is the description. You can see that, for example, the lowest rank generator of this ring has dimension 2, degree 2. This is exactly the smallest manifold which is not boundary of something else, RP2, that we have found in the very beginning of the talk. And then, yeah, you have generators in every degree except the special cases where we have 2 to the power of n minus 1.
Moreover, in this particular case, you have a spectrum ML, which is in fact
Mm-hmm. Yeah.
basically it's just a coincidence. Other coordinates, there are other coordinates in the spectrum which are not
Mm-hmm. Yes, so if you're interested in the full computation, you can check the paper by Malkiewicz, which I have, Malkiewicz-oriented cobordism. It's only 22 pages, if I remember correctly, and they make the explicit computation of this. It's kind of hard to read because they, again, define a lot of heavy machinery in pretty fast succession, but if you know most of it, like Steenrod operation and Hopf algebras, then it should be pretty easy, hopefully.
Okay, well, thanks Anton, thank you for the presentation, and other questions? No, any questions? Well, then
Мгм.
Значит, Егор,